In this question we need to find the net electrostatic force experienced by the charge Q at the vertex of a right-angled charge formation with three charges. It's helpful to adopt a double subscript notation where the first subscript is the object experiencing the force and the second subscript is the object that is exerting the force. So in this particular case, FQR means the force exerted on charge Q by charge R. And similarly, the force pointing to the north that you can see here, FQP, is the force exerted on charge Q by charge P. We'll need to pay attention to unit conversions in this question, so remember that nano means 10 to the minus 9. And there's another one that we'll need to take a look at, centi, in the centimeters, and that means 10 to the minus 2. We need to take into account that Q is negative and P and R are both positive, which is how we had those directions to the north and to the east in the first place. Solving for the electrostatic force is a simple matter of making use of Coulomb's electrostatic force law, where we make sure we've done our unit conversions correctly. We simply substitute the available charges and distances into Coulomb's law expression, and then we get that the force on Q by P is 0.01 newtons to the north. When we do the same thing for the force on Q by R, let's just speed this up a bit, we can see that we get a force that is 0.0018 newtons to the east. And note that we've paid attention to unit conversions, so nano 10 to the minus 9 and centi 10 to the minus 2, and it's important not to forget to square the radius or the distance in our denominator. Now, once we've got these two forces, we still need to actually get the net force. So we need to make use of something called vector addition in 2 dimensions. These are vectors. They're not normal numbers. We can't simply add them like normal numbers. So we need to make use of geometrical and algebraic methods to add these two vectors. The 0.01 newtons, the force on Q by P, is to the north. FQR, the force on Q by R, is to the east. Fortunately, those are at right angles, so to get the magnitude, which you can see over here, we simply make use of Pythagoras. So the net force in magnitude is the square root of the sum of the squares of the other two forces involved, so we get 0.0102 newtons, and to solve for the direction we need to make use of basic trigonometry. So in this case, tan is probably the easiest trig function to use, tan being your opposite over your adjacent, so the angle is then inverse tan of your opposite, FQR, divided by your adjacent, FQP. We get 10.2 degrees. Now to express your net force, the vector, we need to express its magnitude and its direction, and its direction we can say is a bearing of 10.2 degrees, but there are other ways we can express this direction as well. Here's a new diagram coming up to show you this direction. The one way of thinking about the net force is that it's 10.2 degrees to the east of north, but you could also think of it as 79.8 degrees to the north of east. So these are two alternative ways of expressing the direction of the net force.